Hello, hello, hello. This is Nicholas, and today I'm going to be talking about a pretty powerful result of partial derivatives known as Clairaut's theorem, not Clairaut's, Clairaut's theorem. And the idea is that if we've got f, a function f, it could be of n variables, but for now we'll just consider it with two variables, f of x, y. And it's on some disk D. So just to spell it out here right now, a disk D, if we have a circle D, so let's say we have x squared plus y squared equals r squared. So this is a circle of radius r, but a disk of radius r would be x squared plus y squared is less than or equal to r squared. So the circle, it contains just the circumference. The disk contains everything inside along with the circumference. That's the difference, just to be clear there. So if f of x, y is defined on a disk D, which contains the point A comma B, and we have f sub xy, I'll explain what that means in a minute, and f sub yx, I'll explain in a minute, are continuous on this disk D, which contains AB, then what we can say is that f sub xy of AB is equal to f sub yx at AB. And that's the crux of the theorem right there. And so basically what it's saying is that if you've got functions that are defined nicely with second partial derivatives that are continuous, the order in which you take the partials, first with respect to x and then with respect to y, or first with respect to y and then with respect to x, does not matter. So just to spell out what I mean by f sub xy, I've always found the notation to be displeasing, but basically f sub xy means I take the partial with respect to x of the partial with respect to y of our function f. And then likewise, f sub yx means I take the partial with respect to y of the partial of f with respect to x. So in the first case here, I take my function f and I partially differentiate with respect to y, and then I take that answer and I differentiate it with respect to x. What Clairaut's theorem is saying is that if the function's on this disk D, and we just really use a disk out of convenience, you'll see in the proof that it doesn't really have to be a disk, we just choose a disk because I guess it's nice. But if they're continuous and they're nice, in other words, then if I take the partial of f with respect to y and then take that answer with respect to x, it's the same thing as taking the partial of f with respect to x and then taking that answer with respect to y. So as an example, let's consider, well, I don't know. In the last video, I did f of xy is equal to x squared plus y squared, this paraboloid. So let's use that example. If I take the partial with respect to x, I get just 2x. If I take the partial with respect to y, I just get 2y. Now, if I take this here, the partial of f with respect to x, and then I differentiate that with respect to y, I get that f sub xy. In other words, the partial with respect to y of the partial with respect to x. I'm sorry, my bad. I flipped it around on you. This would be f sub y x. So I'm differentiating first with respect to x, and then I'm going to take that answer and differentiate it with respect to y. So since 2x is a constant with respect to y, I just get 0. And then likewise, if I take the partial with respect to x of the partial with respect to y, which is that right there, then I get f sub xy being equal to, now with respect to x, 2y is a constant, so the derivative of a constant is also 0. And we can see that these two derivatives are equal to one another. And it's not just 0 that they always turn out to be. I just gave that as an example, but 99% of the time, these mixed partials are continuous. And we can actually generalize Clairaut's theorem. For example, it doesn't just stop at the second partial derivatives. For example, given the same initial conditions as with the second partial derivatives, we could also claim that f sub x xy equals f sub xyx equals f sub yxx. And so in other words, for partial derivatives of order 2 or greater, however you take the partial derivative, if you do with respect to x, with respect to x, with respect to y, or with respect to x, with respect to y, and then with respect to x, however you take the partial derivatives, whichever order variables you differentiate with respect to, you will still end up getting the same result given the initial condition of continuity. So let's actually prove this result. Remember that in the previous video, I said that the partial of f with respect to x, for example, and let's say of the point x naught comma y naught, that was originally defined as the limit as h goes to 0 of f of x plus h comma y minus f of x comma y over h. Here I'm going to use an alternate definition of the partial derivative. It is almost exactly the same as the alternate definition of the derivative from Calc 1, and it will be as follows. It'll be the limit. Also I should have. So I'm going to get rid of this, and what the new definition I'm going to use is the limit as x approaches x naught of f of x naught comma y naught, of x naught comma y naught minus f of x comma y naught, so no y naught there, or no sub-zero on the, no x naught here, there's just an x, over x minus x naught, over x naught. Okay, let me try that again. Okay, it's going to be the limit as x approaches x naught of f of x comma y naught minus f of x naught comma y naught over x minus x naught. Okay, so sorry about that. So what do I mean by this? So this is just basically saying the same thing as what I said before, and it's very similar to the definition from Calc 1. Recall the definition from Calc 1 was the limit as x approaches x naught of f of x minus f of x naught over x minus x naught, and that was f prime of x naught from Calc 1. So you can see the similarity here with a two-variable function. And so still here, y is just held as constant, because recall from the previous video that we're taking cross-sections along this multivariable function, and that's what the whole idea of the partial derivative is about. So likewise, the partial of, the partial of f with respect to y, evaluated at x naught comma y naught, would be the limit as y approaches y naught. And here x is going to be held constant, so it's f of x naught comma y minus f of x naught comma y naught over y minus y naught. And so these are the two definitions I'm going to use. Now, here's where it starts to get a little, with the variables, get a little variable heavy. So now, let's say I'm going to take f sub yx. So the partial, I'm going to take the partial with respect to y of the partial of f with respect to x. And I'm going to evaluate it at the point x naught comma y naught. Since I'm considering x naught y naught, let me change this up here. Let me change my a to b to x naught comma y naught. And then likewise here as well. Just to be consistent with my variables is all. So now, take the partial with respect to y of the partial of f with respect to x evaluated at x naught comma y naught. That would be the limit as y approaches y naught, because here I'm taking the partial with respect to y of some partial of f with respect to x. So that's going to be of f sub x of x naught comma y minus f sub x of x naught comma y naught all over y minus y naught. So what I did there was I'm taking, see, I already had the partial of f with respect to x. That's why I included this part right here. But then I'm plugging in basically for here in this definition of the partial of f with respect to y, instead of f of x naught comma y, I'm plugging in the partial of f. Or I'm sorry, I'm plugging in the partial derivative of f with respect to x of the same point, x naught comma y, because I've already differentiated partially with respect to x. Okay, so now we're going to expand this out. So, because each of these have their own limit definitions as well. So this is the limit. Here's where it's going to get a little messy. It's the limit as y approaches y naught of, now I'm going to put this in its limit form. So that's the limit as x approaches x naught of f of x comma y minus f of x naught comma y over x minus x naught. So again, y is held as a constant there, and x is varying, minus, now I'm going to do the limit definition of that. So I get the limit as x approaches x naught of, now I'm going to get f of x comma y naught minus f of, oh boy, I hope I have enough room, f of x naught comma y naught. So it's the same over x minus x naught, and then all of that is over y minus y naught from up here. So it, this definition and this definition are here and here, and so realize that these are roughly the same, except now, so in this first definition here, x is the variable, y is the constant, but now y is just held constant at y in this first definition here, but in the second definition here, y is held constant at the value of y naught, and so that's why we have a y naught here and a y naught there. Okay, so now what I'm going to do is now find f sub x y evaluated at x naught comma y naught. So that is going to first be equal to f sub y of x naught comma y minus f sub y of x naught comma y naught over our x minus x naught. So it's similar to what I did here, except now I just replace my x with my y, and I replaced the y minus y naught with the x minus x naught, because now we're differentiating the partial of f with respect to y. We're differentiating that now with respect to x. And so it's going to look, I'm going to shift this over some, because I realized I didn't have much room. So now this is going to be the limit as x approaches x naught of the limit as y approaches y naught of, now, so y is going to be the variable, so we will have f of x comma y minus f of x comma y naught over y minus y naught minus the limit as y approaches y naught of f of x naught comma y minus f of x naught comma y naught. And that's going to be over y minus y naught since it's with respect to y. Then all of that is going to be over x minus x naught. So now what I'm going to do is I'm going to just lightly algebraically mess with that limit definition and this big limit definition. So what I'm going to do is I'm going to multiply this first one by x minus x naught. So by x minus x naught over x minus x naught. That's what I'm going to do to that first one there. And then I'm going to multiply this second one here by y minus y naught over y minus y naught. And then that's going to multiply the second one here. So when I do that, I get that f sub yx evaluated at x naught comma y naught is going to be the limit. And then also what I'm going to do, we'll still have y approaches y naught, but now what I'm going to do is I'm also going to combine these two together because the difference of limits is the limits of their difference. So what I can do is make this just the limit as x goes to x naught of, and now I'm multiplying by an x naught over x minus x naught over an x minus x naught. So that's going to get rid of those denominators there. And then we'll just have a factor of x minus x naught on the bottom here. So okay, now the numerator will now be we're combining these right here since the limit of a difference is the difference of the limits. And so notice what will anything cancel out? No, it won't. So that's fine. So we have the limit as x approaches x naught of f of x y, of f of x y minus f of x naught comma y minus f of x comma y naught, and then it's plus because this is a negative and that's a negative, plus f of x naught comma y naught. Okay, and so likewise what we'll find is that the limit, or f sub xy evaluated at x naught comma y naught, that's going to be the limit as x approaches 0, or as x approaches x naught, my bad, of, and now actually what I can do here is I can write this one, what I'm going to do, the limit as y approaches y naught of the limit as x approaches x naught of all of that. And then here I'll write the limit as x approaches x naught of the limit as y approaches y naught of, and then likewise we'll have f of x comma y minus f of x minus f of x naught comma y minus f of x comma y naught plus f of x naught comma y naught, because from our big limit definitions, this part of the numerator of the numerator, and this numerator of the numerator were exactly the same. So plus our f of x naught comma y naught, and then I multiplied by, instead, a y minus y naught over y minus y naught. So I already had an x minus x naught on the denominator, and then I multiplied by another factor of that. And so now here is the crux of the proof. Since we assume the mixed partials with respect to x and then y, or with respect to y and then x, since we assume them to be continuous, the order in which we evaluate these limits doesn't matter, because since they're continuous, we can just directly substitute in and get some numbers. And so in other words, the order in which we evaluate these numbers for our limits isn't going to matter, since we assume continuity. So we can then flip these, and then we're going to get that f sub yx equals all of this shmazkin, and that f sub xy equals all of this shmazkin. But if we just on f sub y or on f sub xy just flip the limits so that we have first the limit as y approaches y naught, and then the limit as x approaches x naught, then you can see clearly that f sub yx and f sub xy are equal at those points. And so what does all of this say? It says that f sub yx of x naught comma y naught is equal to f sub xy evaluated at x naught comma y naught. And that proves Clairaut's theorem right there. So maybe just as one more example, actually evaluating some derivatives here with Clairaut's theorem, let's use the example used earlier. Let's pick a different one. I don't know. Let's see, maybe I have a function written down already. Oh, okay, here's one. X e to the xy. So first let's find partial of f with respect to x. That gives us, now, x is the variable, y is the constant. So here we have to do a little product rule. So I can first take the derivative of this, and I just get e to the xy. And then I can take the derivative of that part. So that's going to be a plus xy e to the xy, because I have that factor of x out front. And then when I do the chain rule, the derivative of the partial of f with respect to x of xy. So x is the variable, y is the constant. So when I differentiate, say, 7 y, or when let's say y is 7, for example, I'm just pulling these out of thin air. If I differentiate 7x, I get 7. And so in general, when I differentiate xy, I would just get a y, and so this y comes out front here. So that's the partial of f with respect to x. The partial of f with respect to y is going to be equal to, well, this one will be easier, right? That's just going to be x squared e to the xy, because I have this factor of x, and then I take the derivative of xy on the exponent of that e there, and that gives me another x with respect to y, and so then I have x squared out front. Now, if I were to take another way, you'll see these written by, so now this is f sub x, and this is f sub y. So now, if I were to find f sub yx, so take this and then differentiate with respect to y, I get x e to the xy plus, now for this part I'm going to have to use product rule again. So let me view this x times y e to the xy. Let me view it as x times y e to the xy. And the reason why I'm doing that is because x is just a constant, so I don't really have to worry about it. If I can just take the derivative of that and then just multiply the whole thing by x, it would be just as easy. You don't have to think about it like that. I just think it helps me. So, yes, hello, Raymond. So I can get plus x times, now I can take the partial of this with respect to y. So now I use the product rule. Let's first take the derivative of that part. We just get e to the xy. Now take the derivative of this part. We get, if I take the partial with respect to y of this top part, this xy part, then I'm just going to get an x. So I get x, y, e to the xy. And now if I take the part, if I now take the partial with respect to x of the partial with respect to y, which is that, what do I get? Well, I get just a, I need to use the, what? I need to use the product rule because, so first I need to take the derivative of that. So that gives me a 2x e to the xy plus, now I take the derivative of that with respect to x, and I get a x squared y e to the xy. And so notice if I simplify f sub yx, I get x e to the xy plus x e to the xy, so 2x e to the xy plus, and now I multiply it through by this x, plus x squared y e to the xy. And if I take f sub xy, I get 2x e to the xy plus x squared y e to the xy. And these two are exactly the same. And I knew that they would be the same because exponentials times polynomials are continuous for a disk of radius, quote, infinity. In other words, they're continuous for all values of x and y. And so therefore, by Clairaut's theorem, they would be the same. So I'm really just verifying Clairaut's theorem here. I hope that this video has been helpful. I think with